Sir, shall we start the session, sir?
Yes, yes. We are already late.
Yes. Good afternoon to one and all. I welcome our resource person, Dr. Durbadal Mandal, Professor, EC Department, National Institute of Technology, Durgapur. Sir has graduated from RE College of Engineering in Durgapur. He obtained his postgraduate degree in telecommunication engineering from NIT Durgapur. He did his doctorate in engineering in NIT Durgapur. He is having an experience of more than 20 years in academics and research. His area of interest is on antenna optimization, signal processing, and soft computing. SAR has completed the funded project from SERP under the title of Studies on Novel Optimization Technique to Synthesize Radiation Pattern of Antenna Arrays and Design and Implementation of Time Modulated Antenna Arrays with Optimal Radiation Pattern in both transmission and reception. He has published 97 papers in SEA as well as Scopus Index journals and 142 papers in international conferences. He has authored the book titled Nature Inspired Optimization in Antenna Array System, Collective Animal Behavior Based Optimized Null Placement in Time Modulated Linear Array Antenna Arrays. He is guiding more than 20 scholars, among the 12 has completed their research work and 8 has to do 8 is reading their research under his guidance. SAT has got many awards and recognitions. So few are. He is a editorial board member for Applied Soft Computing in Elsevier. He received a Best Paper Award in IEEE Act 2014. Among the top 10, he received the most outstanding researchers in the field of engineering in 2017-18, awarded by Carious 360. In the list of top 2% of scientists in the world in all disciplines during a single calendar year in 2019, based on the Stanford University study, he received the Best Scientist Award. I request Sir to take over the session. Hello, sir. It's not audible, sir.
Am I audible now?
Somewhat, sir.
Now am I audible?
You're audible.
Now?
Yeah, okay, sir.
Now it is okay?
Yeah, okay, sir.
Okay.
Present is also visible, sir.
Okay. So let me start. So a very good afternoon to all of you. So today this is the topic, basically synthesis of time modulated antenna array using ML algorithm. So basically we'll use the some evolutionary optimization technique, that is some meta heuristic technique, that is the one part of the subset of the machine learning, and we are applying that technique for synthesizing the time modulated antenna array. So basically there is the, due to this era of the wireless communication, all of we are using the antenna in our mobile phone, or we can see there is the in the mobile tower, or the in the coming future in there is the 5G. So we need to do a lot of things on the antenna radiation, because for the 5G we know there is the some sort of the power minimization or power optimization is there. So a lot of optimizations are required for antenna, and due to the advantage of the antenna array, basically instead of growing the research on the single antenna element, our group is working on the antenna array. So let me first will give some basic idea of the antenna, and then we'll go for the few results which are already published by my research scholars. So if we go for the what is antenna, so basically there are a number of definitions are there. As you can see, I have enlisted some of them. Yes. So one is the antenna is defined in the Webster dictionary as a usual metallic device as a rod or wire for radiating or receiving radio wave. So there is the similar definition is there for the IEEE standard is also, or in the different book. In other words, that is the an antenna is the interface between the radio wave propagation through space and electric currents moving in metal conductor used for the transmission on the receiver. So basically for the transmission purpose or the receiver purpose, as we are using in mobile phone or there is the in some mobile tower, so that purpose we are using the antenna. So different sort of antennas are there. If we go for the basics of that, there is the wire antenna, there is the aperture antenna, microstrip antenna, reflector antenna, array antenna. So different categories are there. And for an antenna, some parameters are there. So basic parameter, what are the basic parameter? That is the or the different properties. There is the radiation pattern. Radiation pattern is what? That is a mathematical function or a graphical representation of radiation properties of antenna as a function of space coordinate. That is the for a particular direction how the radiation signal is going. So that depending on that, there is the radiation pattern we will measure. So there is the some terminologies are there. There is the field pattern. Field pattern basically that represents a plot of the magnitude of electric or magnetic field as a function of angular space. Similarly, the power pattern. So obviously with respect to field pattern, that is the square of the magnitude pattern. So power pattern can be in the linear scale as you have seen here in the second figure, or power pattern can be calculated in terms of the dB also. So basically this power pattern we need to calculate because sometimes we see there is the radiation power. If it is the less, we cannot receive the signal. So how much received power we can get, so that we need to calculate. And for optimization of an antenna array, so there is the some part, there is the radiation pattern. What is there? There is a major lobe, as you can see here. This is the portion where is the, we can take the major lobe. There is the similarly the half power beamwidth. Half power beamwidth basically the where the power is the half, with respect to that bandwidth is basically the half power beamwidth. And similarly there is the first null beamwidth. If we go for the point to point, that is the first null point, then there is the first null beamwidth. And similarly there is the term minor lobe and the side lobe and the back lobe. And basically out of this radiation pattern, if we go for the radiation pattern analysis, then this minor lobe or the back lobe or the side lobe, that are basically the undesired one, and main lobe is the desired one. Sorry. So for our synthesis process, major target is to concentrate on the major lobe, or there is the reduction of the side lobe and the that is the minor lobes. So in the linear scale also, in the so the polar diagram we can see in the linear scale. So there is a radiation intensity we measure, there is the major lobe, and half power beamwidth, there is the half where the power is the half of the 3 dB point. So that is the respect half power. And similarly the first null, if you go consider the radiation pattern, so it is the looks like there is the some peaks are there. So main peaks is the basically major lobe, which is the our desirable one. So this portion is our desirable one, whereas obviously all these parts are the unwanted one. So these are to be controlled, and that are the side lobe, and similarly there will be the back lobe. So that definition I have written here. There is the major lobe, there is a radiation lobe in the direction of maximum radiation, and similarly the minor lobe, there is the any lobe except the major lobe. So that is the undesired part. Similarly there is the side lobe, so that is the radiation lobe in any direction other than the intended direction, and the usually it is adjacent to the main lobe and occupies the hemisphere in the direction of the main beam. So that are the undesired. Similarly, for which region we will consider? So if you consider the region of the, if we consider the region, then we can see with respect to the antenna one, here we have shown this is the antenna, that is the first one, this part is there. Then there is the, if you take the R1, so that R1 is basically we have taken the reactive near field region, and next one is the radiating near field region, and there is the far field region. So there is the one definition is given. So what is the reactive near field and the far field? If we go, so reactive near field region, that is the region immediately surrounding the antenna wherein the reactive field predominant, and radiating near field, that is also the same thing, but we are similar thing, but we are concentrating on the far field. So what is the specialty of the far field? That is the region of the field of an antenna where the angular field distribution is essentially independent of the distance from the antenna. So that means that the field distribution will be the independent of the antenna dimension and the distance. So that is the this sky color region. So we are mainly concentrating, or the most of the people we are in this region where there is the radiation pattern, or there is the field pattern that is independent of the distance. That is the region, that is the far field, the region of the field of an antenna where the angular field distribution, that angular field distribution is essentially independent of the distance from the antenna. So similarly, we can take the radiation density, radiation intensity, and the beam width. Different parameters are there. So half power beam width already we have discussed. So now the question, there is the antenna array. So what is the antenna? That is the a set of antenna elements arranged in space whose outputs are combined to give an overall pattern that can differ from the pattern of individual element. So that means we can arrange the different elements, in number of elements, in a particular geometrical structure. So that may be in a same line. So if it is the same line, then we can consider that is the linear array. Similarly, if we take that is all the elements we are placing in a circular surface, so that is the circular array. So similarly, we can go for the square, hemisphere, that is the rectangle. So different, there is a different geometrical structure is possible. So instead of taking the single element, we can go for the a number of elements with a specified geometrical structure. Now the question, why we'll go for the antenna array? So that is the increase the directivity without enlarging the size of the single element. So basically directivity. So for this presentation, as much as possible, I have tried to avoid the mathematical part. So I'm not going for the details mathematics of the directivity. So directivity, we can consider that if the directivity of a antenna or the antenna array is more, then obviously we can cover the more distance, or we can go for the, as the name suggests, the directive. So if we like to increase the directivity, then obviously either we need to increase the dimension of the antenna, or we need to increase the number of element. So obviously if it is the dimension of antenna increases, then there is a lot of problems are there, space is there, design problem is there. So instead of going to increase the size of the dimension of the antenna, we can go for the increasing the small size number of elements, so that we can get better radiation pattern or the better directivity. Similarly, there is the next point we written, that is the to achieve the higher gain, that is a single element antenna. So with respect to single element, we will go for the higher gain. So if the gain is high, then obviously at your receiver or if at your mobile set, we can receive the more stronger signal. So obviously to get the more signal or the strong signal, obviously we'll go for the gain should be increased. So similarly, to steer the main beam responsive to a desired direction. So as the presently different communication system is that is the it is desirable or demands that is the a particular direction, we like to steer the beam to a particular direction, that is the will go for the communication of a particular position. So for that case, obviously that is the direction also can be controlled by using the our antenna array. So similarly, to cancel out the interference from a specific direction. So if there is the some unwanted signals is coming, then obviously we need to cancel the signal at a particular direction. For that case, we can go for the null placement. So that is also easily possible by using the antenna array. So these are the few advantages are there. And to obtain these parameters, there is the high gain, high directivity, beam steering, or as you mentioned, there is the cancellation of the interference. So to obtain all these, we need to control some parameters. So what are the different parameters are there if we go for any antenna design? So first parameter is there, as you mentioned, the antenna is basically geometrical configuration. So the geometrical configuration of the overall array. So what radiation pattern will be obtained from the linear? Obviously some circular we can get the different thing. For rectangular also we'll get the something else, spherical, etc. So different configuration we can consider for a particular application. So depending on the application, we can use the different configuration, or there is a depending on some advantage, disadvantage, we can use the suitable configuration as per the requirement. Similarly, the relative displacement between the elements. So if we go for any geometrical configuration, then obviously if we take the linear configuration, that means the all the elements we are placing in a straight line. So what should be the separation between the each and individual elements? So that also we can control, because ultimate total radiation pattern is the vector summation of the individual element. So if you take the individual element, so their vector summation is depends on the final output. So obviously how we are arranging and how much spacing is there, that also matter. And there is the some other parameter is also there. There is the back lobe, or there is the mutual coupling. So different parameters are there. So considering all these parameters, we need to optimize that is the what should be the minimum or maximum spacing. And if you go increase the spacing enormously, then obviously the array size will be very large. So for that case, design complexity will be more. So that also we need to optimize. There is the how we can choose the suitable measurement, or the how you can choose the suitable interelement spacing. So there is a second or third one is the excitation amplitude of the individual element. So when we'll go for the antenna design, so for that case, obviously there is some current excitation is required. So if you give some signal, electrical signal, so how much signal will give, what should be the signal amplitude? So that also we can control to control the output signal. Similarly, the excitation phase, if you give the any electric signal, obviously it has some magnitude and as well as the phase. Then there is the relative pattern of the individual element. So we can take the relative pattern. There is a different element. If you take the dipole element, if you take the microstrip element, so each one have the different radiation pattern. So these are the different few configurations. There is the controlling parameter by controlling which we can get the our desired radiation pattern what we read here. And generally, instead of going to the calculating the total vector summation of the all the elements, if you take the suppose 10 element microstrip antenna or 10 element dipole, so instead of calculating all, we can calculate the parameter that is the array factor. Because for the array factor, one advantage is there, that is the one theorem, that is the pattern multiplication theorem. So if we like to get the overall radiation pattern, for that case, if we know the array pattern of the overall one, the array pattern of the total system, whether it is a linear or circular or rectangular, then we can find out the total array pattern of the system by knowing the one single element. That is, if you know the array factor, then you can multiply the pattern of the single element, then we can get the total system radiation pattern. That is the advantage of the pattern multiplication theorem, because the array factor, that is by considering the isotopic one. So as we are considering the isotopic one, so with the isotopic, if we multiply the individual element pattern, so that will gives the that particular element structure. So obviously for that case, one thing to be maintained, that all the elements should be in the same type. If you take the suppose all of the our microstrip, so obviously if all should be the microstrip, the 12 elements, all 12 should be the microstrip, or all 12 should be the our the half wave dipole, or whatever you take. So by that way, by calculating the array factor, we can do. Now the question, which topic we have mentioned, that is the time modulated antenna array. So basically for time modulated antenna array, the definition as you written is the time modulated antenna array are the antenna array whose radiated power pattern are controlled by periodically enabling and disabling the excitation of the individual array element. So how we can control, that is the will make certain element on for a particular time period and certain element to be off for a particular time period, and that to be controlled by some controlling parameter, or that is basically some high speed RF switch we are using. So by using the some high speed RF switch, so we can control the our parameter that is the radiation pattern. So as we have mentioned the earlier in the last one, these are the different parameter controlling parameter we have mentioned. That is the structure, amplitude, phase, there is the element. So in addition to that, we are using the one extra additional freedom or additional parameter, that is the time as a parameter. So why we will go for the, suddenly there is a time also we are including with this, that is the time module antenna array over the conventional array. So for the conventional array there is the time is not included. So antenna array synthesis seeks a set of optimal complex weights and or element location to generate a required beam pattern. And low and ultra low side low level can be realized by tapering the excitation amplitude distribution in antenna array. So obviously to get the low or ultra low side low level, generally we are going for the tapering of the our amplitude distribution. So from the center we're going to decreasing, there is a tapering of the distribution. And if we go for the current excitation, or there is a phase control, or there is a spacing controlling, so for that case in conventional antenna array, the dynamic range ratio, the highest to lowest value of the excitation are rather very high. So if it is a very high, then obviously it is very difficult to control. So similarly, higher insertion loss or the quantization error are the limitation of the phase shifter used in the phased array to manage the phase excitation of the each element. So obviously there is the insertion loss is the one more parameter if we go for the phase control. So we can go for the phase control or the there's a phased array for the optimization purpose, but for that case these are the few drawbacks are there, so which can be overcome by using the time modulated antenna array. That is the time modulated antenna array were proposed as an alternative and promising means of the realization of the low or ultra low side low level, because as you have mentioned that the side low level for a radiation pattern is basically a unwanted portion. So if it is the unwanted one for the major cases, then we need to control that one, and to control that one we can use the time modular antenna array. Obviously some results will show. And in time modular antenna array, a very low or even uniform amplitude excitation dynamic range ratio are required. Some cases if we like to optimize the side low level, so for that case instead of going to the excitation and optimization, we may not go for the excitation optimization. So for that case there is no question of the DRR, there is a dynamic range ratio, so we can go for the only the time as a parameter. So time, if it is a parameter, that is the on time off time, we can control that one by using some control parameter. So for that case all the elements will be the uniformly excited. There's a same current excitation line can be used. Similarly, all the elements will be the uniformly spaced. If you go for the
Hello? So the slide is not moving, it's not changing.
uniform, suppose linear array or the circular array, so all uniformly spaced. So there's a no question of the design complexity. Hi,
Hello? Sir, excuse me, sir.
now
Sir, the slides are not
is changing.
changing, sir. It is only in the first slide, introduction slide itself, sir.
Introduction slide. No, am I audible now?
You are audible, sir.
Audible.
Sir, you are audible. Sir, you can't able to see the
Yes,
slides,
I
sir.
am sharing that one. So am I audible now?
Yes, sir.
So now can you check if the slides are moving?
Yes, sir. Right now, slides are moving, sir.
It is moving.
Yes, sir.
So if you face any difficulty, you should notice me immediately.
Okay, okay, sir.
Okay. So basically, this is the one major drawback of the online system, because I cannot
Obviously,
follow
sir.
your face. That is the, I cannot read you.
Okay,
What happening in your end, I cannot find that problem. Okay.
okay, sir.
So as we have mentioned, that is this is the topic for the time modulation antenna array. So for time modulation antenna array, basically we are introducing time as one of the parameter with respect to the enlisted these parameters, because all these parameters, as you can see here, that the controlling parameters are there. One controlling parameter is the geometrical configuration. There might be the inter-element spacing, excitation, its phase, or there the element type. So different things that which you can control, and we can use the pattern multiplication theorem with the help of the array factor. If you know the array factor calculation, because in the array factor generally we are considering the isotopic element. So if it is the isotopic element, then if we multiply that one with a single element pattern, then we can get the pattern for that total system. So that is the main advantage of the pattern multiplication theorem. So for that case, only the restriction that all the elements should be in the same type. So if it is the same type, then only you can go for the multiplication theorem by using the single element multiplication. Now the next part, that is the time modulation antenna array. So for the time modulated antenna array, basically we are introducing one extra parameter, that is the time, with respect to all these parameters as we have shown in the earlier slide. So why we'll go for the time modulated antenna array? So obviously there is the some limitation of the conventional array. So what is the conventional array limitation? As you can see from this slide, that is the, if you achieve the low or ultra low side low level, so for that realization, one thing process is there, the tapering of the excitation amplitude distribution in the antenna array. So if you go for the tapering, so for that case also, what problem is there, if there is the suppose 16 elements or 20, or there is the more than that number of elements are there, so for that case dynamic range ratio will be the very high, because if you go for the tapering with respect to the center element, the first element, last one is the very low. So for that case, some error will be there, or there is the design complexity will be more. And second process, one process is also some sort of time we follow, that is the phase shifting, that is the phased array. So if you go for the phased array, then obviously there will be the problem of the insertion loss, because if you go for the phase, there is the element for the frequency element, there is the some insertion loss is there. So that means if we try to control the antenna parameter, then obviously there is some sort of drawbacks are there. So that can be overcome, that limitation, by using the time modulated antenna array. So time modulated antenna array is giving, there is the low or ultra low wide, there is the SLA reduction, even by keeping the DRR is the constant, that is the uniform excitation. If you take the uniform excitation, only if we optimize the time, then also we can get the low side low level. Some result obviously will show. And for the time modulated antenna array, if we consider a simple on off switch in a predetermined sequence to achieve the low side low level, that is the simply on off switch we can use. And moreover, one extra parameter is here to control or to get the desired pattern. So in that way, we can go for the some design of the time modulated antenna array. Obviously, time modulated antenna array has some disadvantage, as we have listed here in the last para. So that is the time modulated antenna array produces the undesired harmonics. That is the, if we go for the time, if we go for the Fourier analysis of that, we can get some harmonic frequency. And for that harmonic frequency, obviously we get some radiation pattern, and that radiation pattern is known as the sideband radiation. So obviously with respect to the side low level, there is the sideband is also there. So that is the one drawback for the time modulated antenna array, because as time parameter we are adding, so obviously if we go for the Fourier analysis, we can get the some harmonic frequency also with respect to the fundamental frequency. So obviously f0 plus, f1, f0 plus twice f1 and so on, some harmonic frequency will be there. So as much as possible, I tried to avoid the mathematics one. If you require the mathematics part, then you can go through any time modulated antenna array paper. These are the basic paper references there. So there is the origin of the time modulated antenna array. So these are the basically some literature survey from where the time modulated antenna array starts. And more strange one is the, if you follow this graph, then we can see the red graph is basically for the cluster of the sub array antenna. So for the sub array or the cluster array, we can see there is sharp rise is there in the red curve. Whereas the thin array is also there is the little bit research was there with respect to time. Basically, x-axis we have given the time and y-axis we have given the number of publications. And if you consider that, yes, yes,
So slide is not moving away also, sir.
again,
Yes, sir. Only changing.
now is it changed?
Now only it's changed.
Okay, so
Previously,
I'm not going to the full screen. Okay, I'm not going for the presentation mode. Is it okay this mode?
now what?
Okay, so if we follow, there is the number of publication or there is the number of research paper on the time modulated array, then you can observe from the 1996, if we take the graph, then even till 2010 also, 2014 also, there's a very less number of research was there. Whereas if you see this page, then in 1959, first the time modulated antenna array system was proposed. So since the 1959 or 1963 till 2010 or 2015, here I have written the 2000, but even if we follow from 2000 there is started, but till 2010 also there is the very less use of the time modulated antenna array. So what is the basic reason? One might be the reason there is a non-availability of the high speed switching. So basically controlling of the antenna elements is very difficult. And moreover, if you follow the year of the 2000, so after that, basically the evolutionary optimization technique come into the picture. Where is the next slide? Most probably yes, in 2002, the first introduced in 2002 the optimization algorithm for time modulated antenna array system, where side low level SLL and the side band radiation have been simultaneously minimized by different evolutionary algorithm. So when the evolutionary optimization technique, there is the strong optimization technique come into the picture, then only the time modulated antenna array research again has been started, where it was started in the 1969, 1960, 1970, early long back. So this is the one reason that is the why this research has started after 2010 or after 2000 it is started. So similarly, we can see there is the what is the role of this time modulated antenna array. There is the main beam is there, and as you can see, these are these dotted or these graph basically for the sideband pattern. And for this optimization to minimize the side low level, some optimization techniques are used. Initially, they have used the D technique. So for optimizing any parameter, obviously we require some fitness function or the cost function, which function to be optimized. So for that purpose, basically we can write down that is the cost function is there. So this cost function is chosen. So for this cost function, what is there? First is the theta BWFN, that is the first null beam width. So it is the first null beam width. Then there is the side low level. Then there is the side band level. So if we consider the first null beam width, that is the this portion is sorry not yes first null beam width, that is the this total width, because main lobe should not be sacrificed. You will not sacrifice the anything against the main lobe. So for that case, obviously we will take the width of the main lobe as an optimization parameter. Then one parameter we have taken the sideband, and similarly we have taken the one parameter that is the our side lobe. So that three parameters we have listed here. One is the first null beam width, then side lobe level, then sideband level. So these to be optimized with respect to the our radiation pattern. So this is the obviously side lobe level with respect to the fundamental frequency, and sideband with respect to the harmonic frequency. So F0 plus some harmonic frequency. So as you have mentioned here, there is a theta BW in the main lobe beam width between the first null and the center frequency. Side lobe level, that is the calculated maximum side lobe level at center frequency F0. Similarly, SBL is the maximum side band level at the first sideband frequency. So this is the some flow we have given. There is the how it is under the machine learning. So if you go for the machine learning, there is the two different type. There is the uninformed, informed, and the informed search. So this is under the informed search. There is the heuristic, and this is the some sort of meta heuristic we are taking. So antenna plays an important role to channelizing the electromagnetic radiation for useful purpose. And for modern age wireless communication, the 5G or the beyond 5G, antenna array are the very important, and especially for the beamforming features, because you have seen there is a for the 5G will not radiate the signal 24/7. So beamforming is required for that case. So that beamforming can be achieved by using some antenna array. And for this purpose, obviously some pattern synthesis is required. That is the how we can get the maximum radiation of the directive one, because will radiate at a particular direction for a particular duration. So obviously that pattern should be synthesized. So for the synthesis of the antenna array is not an linear problem. This is the multi-objective problem, because the some gain enhancement is required, directivity should be enhanced, beam steering is required, some side lobes should be reduced. So there is some multi-objective problem we can go. And for that purpose, we can take different sort of the evolutionary optimization technique, because if you take the classical optimization technique, so it has some drawbacks as we have listed here. There is the highly sensitive to the starting point, that is the size of the solution. Similarly, the frequent convergence of the local optimal solution. So if you start for a particular point and suppose there is the number of optimal points are there, that means if it is the multimodal function, so for that case there is the high chance for the stuck at the local optima. It is the unimodal function, then no problem. And similarly it required the continuous and the differential equation. If you go for this, for the optimization generally we are using the first order differentiation, second order differentiation, and so on. So that means the function must be the differentiable in nature and function should be the continuous. But if you follow this antenna problem or there is the any design problem, that is the discontinuous one. Similarly, it requires some linearity. Or if you go for the optimization by using the classical one, if there is the variable 1 2 3 4 or that one, that is easy to calculate. If there is the number of variable is very high, so for that case it is very difficult to optimize that one. So due to this some sort of the limitation, we are basically going to the some evolutionary optimization technique. So for the evolutionary optimization technique, or it is also known as the nature inspired optimization technique, so that is the these methods are inspired by the some phenomena from the nature. So these methods are mainly a population of the potential solution, and better individual selected for reproduction and their offspring replace worse individual. That is the by using the evolutionary optimization technique, what is the basically we will follow. That is the instead of taking a particular solution, and we are going to take a solution set. That is the from the solution space we are taking the a set of possible solutions within that range, and out of that set of possible solution we are finding the best one, second best, third best, and so on. And we are replacing the worst one with the help of the some offspring, as you mentioned, offspring the which we can generate from the some best solutions, and we will discard that worst solutions with the help of the good quality offspring, and we will repeat the process. So basically this is the basically evolutionary optimization. So continuous evolution is going on, and by using that evolution process we can find out the near optimal solution. That might not be the exact solution which we can obtain by using the classical method if possible, but that is some sort of the robust solution or the near global solution can be obtained. Only the thing that is the for this sort of process or the evolutionary optimization technique, basically it might be some time consuming, and there is the number of parameters. If there is a more number of parameter, there is no, till now there is no mathematical guideline as to how we can control all these parameters. And similarly, it is highly depends on the problem specific. So for a particular problem, one evolution optimization technique might works very good, and for the other problem, it might not works at all. So there are these some sort of the limitations are there, as you have listed here. There are the drawbacks. So some sort of drawbacks are there. But one major advantage is, as you told, if there is a function is not totally defined, if the function is not continuous, if there is the number of solution is required is the very large, then also we can use this technique. And moreover, same evaluation technique or the same program if you can write down, that can be applied for different type of problem, whether that is the antenna problem, signal processing problem, or the VLSI problem, or the power system problem. Whatever the problem, basic structure we can use the same one. So these are the few advantages are there. So we are basically using some evolution optimization technique for the antenna optimization for this one. This is the theory of the linear antenna array. So if we take the linear antenna array, as you have mentioned, that the array factor. So array factor is a function of, this is the equation. In is the current, as we have mentioned here. The d is the spacing between the radiating element, k is the propagation constant, n is the number of elements, in is the amplitude acceleration of the nth element. So this is the basic equation for the linear antenna array. And with that, if you add the time as a parameter, so after applying the time modulation, so obviously we are applying the time as a parameter, that is the, we have mentioned the un of t. So where un of t is the periodic function of the time sequence. So that means with the original radiation pattern of the antenna array or the array factor, will multiply the time as a parameter. So if we apply the time as a parameter, so then obviously this is the structure representation. So obviously if we make that un equals to some time it is the 1, then obviously the array factor will be the 1, because there is the un is multiplied with the array factor. And if it is the 0, then output will be the off, corresponding to that particular element. So basically how we are taking, there is the, for a particular time period, we are taking a particular time span. This is the, as you mentioned, the basic switching scheme. The determine the switching scheme can be developed for different application of time modulated antenna array. And the most basic switching scheme associated with the time modulated antenna array is simple on off switch. So this is the simple on off switch. First time is the on, after certain time it will be off for a particular time duration. And assuming that the nth element in switched on for an interval of the tn within each period, that is the, if we take the tp is the time period, total time period, and switched off for the rest time period, then unt can be defined. Obviously this is the defined as the tn, tau n is the less than t to tp. So that means that this is the time duration for which that is the our switch is on. So this is the most simple time switch scheme, switching scheme. So next one, some sort of complex switching scheme. There are a number of complex. Hello. Yes. Any question? So there is the some complex switching scheme is also there. A more complex switching scheme, as you see here. So that is the pulse shifted switching scheme. So pulse shifted means there is the, instead of the time duration off or on from the starting time, we can take a particular pulse, that is the a gate function. It looks like a gate function, a window. So that means the unt equals to 1 for a time duration of tp, where it is starting from the tn1 to tn2. So that means that we are going for the some pulse shifted switching scheme are useful for the suppression of the undesired harmonic radiation in time modulated antenna array. And this can be presented as you have, you can see there that the unt equals to 1 for a particular time period, and which is not starting from the 0. And similarly we can see some different application, that is the time modulated antenna array for side lobe level, if we go for the side lobe level suppression, there is the time modulated antenna array has been extensively used for the reduction of the side lobe level. And an example we can see for the linear 16 element, this is the result for the 16 element linear array, and you can observe there is the 40 dB reduction is possible for different cases. F0 is the for the fundamental frequency, and there is the F0 plus A pair, that is the first harmonic. Next is the second harmonic. As you mean the case 3 means, there the in the next slide is written. We have taken the different case study. First case study is the optimal switching time sequence of each element. That is, we are taking the time sequence is the optimization, not there is the optimizing the inter-element spacing and the other parameter. So that is the case A. Similarly, case B or case 2 we have taken optimal switching time sequence of each element and optimal non-uniform inter-element spacing. That is, the spacing is not the uniform spacing. For the first case, we are taking the spacing is the uniform. Next one is the optimal switching time sequence of each element and optimal uniform inter-element spacing. So obviously for the case 1 and case 3 difference is what? For the case 1, optimal switching time sequence, and this is the optimal switching time sequence of each element and the optimal uniform inter-element spacing. That is, the inter-element spacing is the uniform, but that is the optimal. But for second case, inter-element spacing is optimal, but it is the non-uniform. So the first element is the, suppose first to second is 0.5 lambda, second to third might be the 0.56 lambda, or third to fourth might be the 0.7 lambda. So that means that spacing is the non-uniform. Whereas for the third case, we are taking the optimal timing sequence is there, but the optimal uniform inter-element spacing. That is, if it is the suppose 0.6 lambda, then all the elements are separated with the 0.6 lambda. So this is the three different cases we have seen, and for that three different case, we can see if it is the visible one. I hope the harmonics are visible. So obviously these are the harmonic frequency, and this is the time that the side lobe reduction is there. But if you follow that harmonic frequency, the radiation patterns, they have the lot of contribution, because there is the power is not the negligible one. That is the roughly the 15 dB or more than, second case the more than minus 20 dB. So if you go for the higher harmonics, obviously radiation power will be the less, but that is considerable for this case. But for this case, we are concentrating on the side lobe level reduction only. So next we can see the separate one, that is the different application for this one also. There is the symmetric time modulated antenna array for side lobe reduction. So how we are doing this one? There is a linear time modulated antenna array with symmetrical antenna array with respect to the center of the array is presented here. So for this case, what we are taking, the references are given for all the cases. So for the details of this one, you can go through. This is the reference is given, which is our published paper in AU. So one part of that results I am showing here. So similarly for this one is also from our reference is given here. So for this case, what we are taking, this is the how many elements we have written. Most of it was for the 16 element antenna array. Yes, for one side it is 8, so it is a symmetric. So obviously there is a 16 element array is there. So if we follow, the center element is on period is roughly 0.98 with respect to, if you take the unit is the 1 first time duration, so 0.98 with compared to the second one is the reducing, third one is the again reducing, fourth one and so on. So that is the time duration or the on time duration is we are tapering. So that means for the side lobe reduction, we are going to tapering of the time duration. That is the eighth element. It is on for the very short time. And by using certain optimization technique, as you mentioned, the NPSOWM, there is a novel particle swarm optimization with wavelet mutation is used in this case to optimize the switching time for half of the array element. Yes, as I mentioned, there is a 16 element. Half of the array element as the array structure is the symmetric in nature and with respect to the array center. So obviously it is taken with respect to center. There is the, this is the, if you take the right side, so obviously in the left side is the same thing, and below minus 55 dB SLL is obtained. So for this case, we can achieve the more than, there is a minus 50 dB, there is ultra low is obtained, there is minus 55 dB SLL can be, reduction is possible. So for this case, all the elements are, the on period is varying. Whereas for the earlier case, if you follow, for this case, we have mentioned the case 3, optimal switching time sequence for each element. So obviously that is not the tapering one, that is the arbitrary one. Similarly, we can take for the time model linear array for the sideband level reduction. So till now, if you follow this last graph, that is the side bands, this is the center frequency. So once again, let me go for the full screen. I don't know whether slide will move or not. So if you take the uniform and the center frequency, there is the green one. And if you follow this red one, there's the first harmonic or the second harmonic. So this power is not the negligible one. This power is also roughly 12 dB or 18 dB or so on. So as we are increasing the first harmonic, second harmonic, third harmonic, and so on, so obviously power will be reduced, but we can consider at least 2 harmonics. So for this case, we are not considering the side band level, that is the power due to the harmonic frequencies. But now we are taking care about the sideband level also. So that is the, we have mentioned that the time modulated linear antenna array for sideband level reduction. So sideband reduction is a concerning issue of the time modulated antenna array, as the efficiency of the antenna sorry, as the efficiency of the antenna is inversely related to it. Then obviously, because if the some power is the wastage power is there, so then obviously that is the efficiency will reduce. So for that, the suppression of the sideband radiation is essential one. That means that if we suppress the sideband radiation, then it increase the efficiency. Because for this case, you can see, if you calculate the power, then obviously this is the our useful power, whereas the sideband powers are the unwanted or the unuseful power. So if we go for this technique, that means if you follow this 30 element array, you can follow from the suppose third, fourth, fifth. So fifth to 24, that is the middle elements, all are the excited for the full duration. That is all the switches are on for a long period. Whereas the edge elements, there is the edge elements, that is the for the this case the first element, and as well as the, if you count the 24th, 25th, so 26th element or the 28th, 29th element, so they are off totally. So few elements are, we are keeping totally off, and for few elements we are controlling the time duration. And for that case, what radiation pattern we can achieve, you can see that one. So this red one is basically the our center frequency one, that is the desired one. So this is the time model antenna array for the sideband level reduction. The radiation pattern of a 30 element array with reduced sideband level is presented. So using the optimized switching sequence. So what sequence? As you've seen here. So this sequence. So if you follow this sequence, then if you follow the sideband level, then with this approach, sideband level for the first and second harmonic are reduced to below the minus 30 with nearly minus 20 dB SLL. So if you follow, there is the, this is the minus 30, this green one first SLL, similarly the SBL, similarly the second one, that is second harmonic H equal to 2, the blue one, that is further reduced. So that means till now what we have seen for the sideband level, that is the, for this case, it is a near about the 12, 13 or like that. For first harmonic, it is the suppose the 12. So for this case, we can achieve to the minus 30 dB. So that is the sideband effect may be reduced. So to reduce the sideband level, we can use this sort of switching sequence. So this is also a simple switching sequence, because most of the elements we need not to control, only the edge elements we are controlling. then we can take the time modulated linear antenna array for the simultaneous reduction of the SLL and SPL. If you notice this figure, then as you have written that the side lobe level is the minus 20 dB, whereas for this case side lobe was the minus 60, near about the minus 55. So that was the sideband was not reduced, but side lobe was reduced tremendously. But for this case, we have reduced the sideband, but not the side lobe. So obviously, for increasing the directivity and the our gain, we need to control both of them. So to achieve that one, that is the to achieve the reduced side lobe level as well as the sideband level simultaneously. So to achieve this, excitation amplitude of each element and sub-array switching scheme for outer elements have been optimized. That is the we are optimizing till now. You can see we are optimizing only the time sequence. So for this case, we are optimizing the time sequence as well as the amplitude also. That is the amplitude of the excitation. So that is first one. If you follow the first figure, this is the normalized amplitude excitation. Second one is the normalized switching time. So if you take the number of element, so in number of element, so starting from the 0 to 16, because we are taking the 16 element. So for this is the time sequence. So if you follow the time sequence, so from the third element to 14th element, basically all the switches are on. And with respect to the first element, if you follow the first element, so on time of the first element equal to the off time of the 15th element, or rather you can say that is the off time of the first element is basically same as the on time of the 15th element. Similarly, off time of the second element is same as the on time of the 16th element. So that means if we optimize only two elements, that is the first and second, we can get the time sequence for the total 16 elements. So that means we are optimizing only the edge sequence as well as the amplitude excitation. And by using that one, if we follow, there is the huge reduction or the considerable reduction in the side lobe level as well as the sideband level, because uniform is the reference one, that is the dotted one, whereas the blue is the m equal to 0, that is for the fundamental. So if we see that fundamental is the, as you written here, the ultra low, that is the minus 40. So obviously side lobe level is the minus 40 dB. And whereas the similarly the sideband level, if you follow, that is the for the red one or the green one. So red one or the green one is the roughly less than minus 30. So that means that by optimizing these 2 points, that is the by optimizing the our amplitude excitation as well as the time sequence, it is possible to achieve the our side lobe level as well as the sideband level controlling, and we can reduce both at the simultaneously. So for that we have taken, this is the our cost function, because for the optimization we need to use some function. So the cost function is the simultaneous suppression of the side lobe level as well as the sideband level of the time modulated linear antenna array. So we have taken the SLL with respect to the fundamental F0. Similarly, we take the SBL, the sideband level with respect to the fundamental plus the harmonic frequency M into F of P. So for the harmonic frequency, if we go for the Fourier analysis, we can see there is the major contribution is from the first harmonic and second harmonic. So if we go for the calculation of first harmonic, second harmonic, then it is sufficient with respect to considering all the harmonics. And then we need to calculate the first null beamwidth, because you cannot change the first null beamwidth. So these are the parameters. Some weighting factors is there. There is the W1 and W2. So depending on the our requirement, suppose if it is a requirement is the side lobe reduction is more important with respect to the sideband, then we can increase the W1. Or if it is the suppose sideband is more, then we can go for the increase the W2. Otherwise you can go for the equal, and that can be obtained from your experience or the by some hit and trial method also, as you can decide. So for this case, as you have taken, for this case, the for this minimization problem, equal contribution have been considered for side level SLL, that is side low level, and as well as the sideband level, because we have taken the equal contribution. So these are the some results we can see There is the from the harmonic search algorithm. So this is the SLL is there. Similarly, SBL, how much SBL is there? SBL for the second harmonic. Similarly, the first null beamwidth, there's the directivity. So some results for the, this is the first one in the first 16 element, second one for the 30th element. So this is the using by optimization techniques, and with the help of the programming, we can get it. So this is the one technique where we can use the time modulated antenna array for beam steering. So what we are doing for this case, a different kind of progressive switching scheme is also developed to steer the harmonic beams into different directions without affecting the main beam. So that means for this, if you follow the graph of the right hand side, so then if you follow the blue curve, so this is the fundamental one. There is the original one, where is the main lobe is the secret, and next is the red one is the first positive harmonic frequency. Similarly, the pink dotted is the second positive harmonic frequency. Next one is the third harmonic, and so on. So, and this is the, we have taken the, if you follow the last one, that is the blue one or sky blue one, that is the first negative harmonic frequency, because harmonic frequency can be the f naught plus f1, or it might be the f naught minus f1 also. So if we consider the negative harmonic frequency, obviously we get the left hand side. So for this case, we are taking the time sequence. If we take the 16 element, so we are dividing total 16 element time sequence, the total time sequence, with a 16 division, and each element will be turned on for a particular duration of the 1/16th of the time. So if you follow this one, then the first element is on for the 1/16th of the time. Second element, after the switching off of the first element, it will turn on, and that will be also turn on for the first 16th, the 1/16th of the time sequence. And third one will be the, there is after the switching off of the second one, third will on, and so on. So you can follow, there is the, all the elements are switching on with a progressive time sequence. So as we have mentioned, there is a different kind of the progressive switching scheme. So obviously the switching scheme in the progressive manner, and if you take the switching scheme in this manner, then harmonic frequency will be steered. So there is some beam steering is possible. So if there is a beam steering is there, so that means obviously these unwanted or unused harmonic frequency amplitude can be also useful, because this harmonic frequency will not affect this main beam, because the main beam direction will be the remains constant. That is, the by fixing that one, harmonics will be shifted with a certain angle, and how much it will be shifted, so that can be calculated from this mathematical expression. For the details mathematical expression, you can go through this paper, it is given. So this is the theta, the how much shifting will be there, there is sine inverse twice m by n. So where the beam pattern at first negative harmonic m equals to -1, the fundamental frequency m equal to 0, and the first positive harmonic m equals to 1 are expressed as. So that is the, if it is the m is the +1, that is the positive harmonic frequency. M is the -1, that is the for the negative harmonic frequency. If we take the m equals to +2, there is the second harmonic. Similarly, -2, there is the negative second harmonic frequency. And n is the number of element. So simply by putting the number of element and the position, we can calculate the theta. So from that expression, we can calculate the how much the first harmonic frequency will shift, second harmonic will shift, third harmonic will shift. So if it is shifted, then we can get the multi-beam radiation pattern is possible, and at the same time, the unused, that the side sideband pattern can be used with respect to the wastage. And to reduce the, or to block the signal from the certain portion, then we can go for the deep null placement. The deep null placement at a desired direction for the steered radiation pattern is also achieved by the progressive switching. So by using this sort of progressive switching, it is possible to get the deep null. So this is the deep null with respect to particular angle, and if we like to get the deep null in a particular direction, so yes, or the wide null, that also can be possible. I hope that is in the next slide. Okay, so time modulated linear antenna array for simultaneous sum and difference pattern, which is useful for the monopole system, that the monopole radar we can use, have been studied. And that is the how we are taking. If you follow this one, this is the first part is the normalized amplitude pattern. So for this is the normalized amplitude pattern, and this is our time sequence. So if you take this is the time sequence, then you can follow the on duration of the first time sequence, that is the off duration of the ninth time sequence. Because this is a 16 element, if you take the 16, so obviously the symmetry with respect to 8. So if it is the symmetry with respect to 8, then on time of the first one is same as the off time of the ninth one. Similarly, on time of the second one is same as the off time of the 10th one. Because on time of the second one, if you follow, then you can see there is the a window system is there. It is on for certain duration, then it is off. At the end, again it is on. Similarly, for the second one is also, if you go for the third one, there is a certain time it is the on and certain time is the on. In between that, there is the off time is there. And what is the off time of the third one? That is basically on time of the 11th one. So that means if you follow the structure, then this portion is basically similar to this on portion. So that means the up to half portion, that is the 1 to 8th. What is the on structure? So that is the off structure of the our 9 to there is the 16. So that means if we optimize up to the 8 element, that is the half of the element, then we can get the result for the rest half or the remaining half. And by using that one, we can get there is the difference pattern and the sum pattern, which is basically used in the that is the monopole system. So if there is the monopole system is there, then we can use this one. So this is the radiation pattern or the structure is given, or this is the basically some statistical analysis is there, power calculation and others. And this is the basically our equation for the optimization, that the simultaneous sum and difference pattern. So SLL and SBL we can take SLL reduction and the functional beamwidth. So obviously for this case we have taken the SLL is the most important one. So we have taken the W1 is the more than the W2. Yes, this one is the for the white null. If you like to block some undesired signal from a particular direction, so we can go for some white null. So for the white null placement, basically if we follow this one, that is the uniform one is the blue one, the center frequency is the green one. Then for the first harmonic, so first harmonic we have taken a deep null is there. Similarly, the second harmonic is also a deep null. So that means that by adjusting the switching sequence, the dual and multiple broader null can also be generated by the formulating the suitable cost function. An example of the creating the dual null, yes, for the yes, for this case, there the dual null is also there. This is the null for the particular duration. Again, another duration is there with respect to the center frequency. If it is the uniform for the center frequency, a particular range, that is for this case, range is given most probably, yes. So 0 to 30 degree, then 50 to 80 degree. On the left hand side, similarly right hand side, 150 to 180 degree and 100 to 130 degree. So there is the multiple dip null is also can be inserted by using the time modulated antenna array optimization. So this technique can be used for the circular array also. That is, if you take the circular pattern. So for this case also we can see this is the circular one. So different case may be considered as the time modulated half symmetrical circular antenna array, or we can take the time modulated asymmetrical circular antenna array if you take. So for that case, some switching sequence, yes, for this case it is mentioned there is a switching time sequence of each element. So for each element 20 element is there, so a particular switching time sequence we have taken. So that means if you count, so this is the time sequence as you have taken in the microsecond. Similarly, the phase excitation of the each element we can calculate, and from that we can achieve the our radiation pattern. And if we follow the radiation pattern, then obviously this green one is the basically our fundamental frequency one. Second, this red one is the first harmonic. Then black one is the second harmonic. And by using the different optimization technique, we can get for the side low level for the different elements, the 20 element, 36 element, or there is the second case. We have taken the two different cases as we have mentioned here. Yes, case one is the for the half symmetric, case two is the asymmetric one. So similarly, that can be applicable for the our concentric circular antenna array also, which we are applying for the circular. So that can be obtained from the concentric circular also. So for concentric circular, we can do for the ring wise, basically instead of taking the element to element, because if you take the element to element, then there is a number will be the huge number. So for this case, if you take the 9 ring, so first ring basically we have taken on time duration is how much you have given, radius, there is the distance, and number of elements is there. If you follow, there is the first ring 6, 11, 17. So different number of elements we are taking and different timing sequence we are taking. So for that case, you can get different radiation pattern. The optimal side low level, first null beam width, directivity for the 9 ring time modulated concentric circular antenna array. So obviously time we have taken the sequence, but not for the each and every element. We are taking the ring wise for this case. So there is some application of the advanced applications are there. So by controlling the switching sequence of time modulated antenna array, more advanced applications can also be achieved. That is the extensive research is going on the time modulated antenna array for the application of the beam forming, the beam steering, direction of arrival, multi-input, there's the MIMO application. There's some radar tracking system. So different applications are basically there. So obviously we are doing a small part of that, not the every aspect we have the expertise. And at the end, I should acknowledge my students. So these are my students who did this work. So what I have basically presented, this is basically done by these 3 PhD students. So one is the Dr. Gopiram. So presently he is the faculty of NIT Warangal. Then Dr. Abhishek Chakraborty is the faculty of the SR University Warangal. And next one is the Abhishek Das. He is the faculty of the HIT Haldia. So I should acknowledge them because basically this is the mainly their work. They have done this one. So as per your time schedule, we have 5 minutes more. I don't know how much time is there. So any question?
Thank you, sir. Dear participants, if you have any queries, you can unmute yourself. And
First of all, this slide is already I have forwarded to your coordinator, and I hope it will be circulated to the faculty members. Participant, is it?
so we didn't circulate right now, sir. After the session, I will send it to the participants, sir.
Okay. No, you are free to share it. I don't have
Yes,
any
sir.
objection for sharing this one.
Okay, sir. I will send to their respective mails.
Yes, yes. So
Okay,
if
sir.
they think, then you can share it.
Oh, sure.
And if any student feel to get some idea, so they can take the snapshot of this page. So you can freely contact to my students. And I hope they are more capable with respect to me to give the guidance about the time order antenna because they have spent much time more than me to do their research, especially these 3 students who did the work on this one.
Dear participants, if you have any queries, you can raise up to sir.
So as usual, I hope there is no query. So let me stop the sharing.
Hello, sir.
Ah, yes, yes.
Yeah, I have posted one query in the chat box, sir.
You have posted.
Yeah,
So
regarding that pulse shifting switching. Hello.
where you have written? Yes, just let me see where you have written.
In pulse shifted switching, sir,
Yes,
if we shift the pulses, will it
yes.
not affect the original signal, sir?
Just let me know. I hope you are asking to this slide. Let me go to the slide. Then it will be better.
Uh,
This one. Is it your
Not,
query with respect to this slide?
not pulse shifted one, sir.
Can you tell me the slide number?
I don't remember, sir.
Actually, I have given the slide number. That's why, so that I can
Uh,
follow this one.
I didn't notice, sir. But actually, the query is on pulse shifting.
Pulse shifting.
Yeah, yeah.
Yeah. So what is your question?
My question is, if we in pulse shifting
Hmm.
switching, if we
Yes.
shift the pulse,
Yes.
will it not affect the original signal, sir? The phase of the original signal will be affected, no, sir?
Phase of the original signal. No. Why?
Yeah. So when
First,
we keep on
first of all, we are shifting the time. These are we are taking the parameter is the time as a parameter.
the
We are
time
not
parameter.
we are not controlling the phase or the amplitude. We are
Oh,
taking the time as a parameter that we have mentioned. That is the major advantage or disadvantage for the time modulation. If you go for the amplitude modulation, there is the shifting of the amplitude or optimization of the amplitude, or there is the phase. So there is some question is there regarding the, as you have mentioned, there is the insertion loss, or there is that DRR is there, dynamic range ratio. But for this time modulation one, we are not touching on the amplitude or the phase. We are
oh.
putting the time, that is the on or off. As
But
we have
offset will be affected, no, sir? Offset.
off switching.
Offset of the signal will be affected if we keep on shifting with respect to time domain, no, sir?
Yes, that is the, that's why we are measuring, there is the sideband. If we
Oh,
go for the shifting of the that frequency, as you have mentioned, this is
oh.
the, suppose if you for this example, there is the sideband will be affected.
Sideband
If
of the original signal,
yes, sideband of the original signal,
not the main lobe.
not the main lobe. But
Oh,
indirectly
oh.
we can say that the main lobe is also affected, because if you go for the, suppose, let me go to one worst diagram. Yes, if you go to this worst diagram, then you can see there is a, this green one is the original desired one, whereas
Hmm.
this one, this red one or this blue one, that's the first harmonic and the second harmonic.
Yes,
So
sir.
if we calculate the gain of the signal, then obviously we'll calculate that one with respect to the first one. But whereas these two power is not the extra power, that is also some wastage which is coming from our input one. So that's why
Oh,
our gain will be reduced for that case,
oh,
as we have mentioned in the very next slide. Yes, that is the efficiency of the antenna is inversely related to it. That is the sideband ratio or the sideband level, as you written, the sideband level is a constant issue of the time modular antenna array, as efficiency of the antenna is inversely related to it. So that means if it is increases, suppose this power is more, so as if we follow my cursor, then this power is obviously some wastage of power, this first harmonic or second harmonic.
hmm.
So obviously efficiency will be less. So for that, basically if you follow this one, we have tried, that is the this first harmonic or second harmonic should be as low as possible, so that it will not affect the original one.
Oh, okay.
Okay.
Thank you.
Or
Thank you, sir.
moreover, if you follow this one, again we have tried the both. There is side low level as well as the sideband also. Because
Oh,
sideband is the basically constant parameter for the time modular antenna array. So
oh,
for, because for time modulation, we are avoiding the amplitude or phase factor.
hmm.
Okay, so if we
Oh,
do that one, then this problem will be there. Obviously, whatever with the system, everyone has some inherent advantage and disadvantage.
okay. Thank you, sir. Thank you.
Yeah, welcome. So any question?
Any more queries? Thank you, sir. Thank you for your effective and wonderful presentation. I would like to thank our resource person, Dr. Durbadal Mandal, Professor,
so
ECE
welcome you all.
Department, National Institute of Technology, Durgapur, on the title Design of Time Modulation Based Antenna Array Using ML. Thank you, sir. Thank you for your extremely informative presentation. It helped us gaining knowledge in the domain of wireless communication. You have broadly covered all the concepts. Surely our participants have taken many valuable things from this session, as well as they can able to implement in their research work also. Sir. Thanks a lot for your presence even in your busy schedule, sir.
So thank you all the participants from my side also for their patience hearing in spite of the lot of interruption due to the net connectivity problem. I don't know how it happened, but it happens. Okay, so thank you all once again. Let me so I am disconnecting now with your kind
sir.
permission.
Yes, sir. Thank you, sir. Dear participants, feedback form is available in the chat box. Kindly fill the feedback form for your attendance. Thank you for your patient listening till session 12. Once again, we'll rejoin by day 5, session 13. Tomorrow, we have a session on USRPS. There is a small change in the session for tomorrow forenoon session 13. The resource person is from NI LabView, Mr. V. Vasantakumar. He is going to handle a session on USRPS. A hardware demo module will be there. So kindly join exactly by 10 a.m. itself. Thank you.